Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Hello friends, here in this video we will study the measurement of capacitance using the Sauty's bridge. Sauty bridge is an alternating current bridge which measures the value of capacitance by comparing it with a standard capacitor. So let us start with our topic. So this Sauty bridge, it is the most suitable method which is used for comparing the capacitance of two capacitors. And as I have said that it is an alternating current bridge which measures the value of capacitance by comparing it with a standard capacitor. So this Sauty bridge, it is mainly used for the purpose of measurement of capacitance. So here it is measuring the value of capacitance by comparing it with the standard capacitor. So we can also say that it can be used for comparing the value of two capacitors. Now as this Sauty bridge, it is an alternating current bridge, so it will consist of 4 arms, and in the 4 arms we have the 4 impedances, that is Z1, Z2, Z3 and Z4. There will be 4 arms AB, BC, CD and DA. And in these 4 arms we will have the 4 impedances Z1, Z2, Z3 and Z4. Okay, so this forms the bridge network. Now out of these 4 impedances, impedances are a combination of resistance, inductance and capacitance. It can be a series combination also and it can be a parallel combination also. So out of these 4 impedances, the Z1 impedance, it will be the unknown impedance which we want to measure, and the remaining 3 impedances, they will be the known impedances. Unknown impedance is the impedance or the electrical parameter which we want to measure. So here we want to measure the capacitance. So unknown impedance will be a capacitor. And the known impedances means the value of these impedances is already known to us. So the known impedances, it can be a capacitor, it can be a resistor or it can be an inductor. Or it can be a combination of these 3, like it can be a series combination or it can be a parallel combination. Now other than these 4 arms, the bridge network, it will also consist of a detector and an alternating voltage source. Okay, so this detector, it is used for obtaining the balance of the bridge network, because we know that the bridge is said to be balanced when the detector, it gives us the null deflection. So detector is used to obtain the balancing of the alternating current bridge, and the AC voltage source, it provides the power supply to the bridge network. So this Sauty bridge, it will consist of 4 arms, 1 detector and 1 alternating current voltage source. So let us see the circuit diagram or the configuration of this Sauty bridge. So this is the circuit diagram for the D-Sauty bridge. In this bridge you can see we are having 4 arms A, B, B, C, C, D and D, A. And in these 4 arms we are having the 4 impedances. This is Z1, this is Z2, Z3 and Z4. So as I said that these impedances, they can be a capacitor, resistor or an inductor. So here Z1, which is the unknown impedance, is the capacitor C1, and we want to find out the value of this capacitor or the capacitance of this capacitor. Now Z3, it is a resistor, Z2 is again a standard capacitor and Z4 is a resistor. Now in between the arms B and D we have the detector. D is the detector and this is the symbol of an AC voltage source. So AC voltage source is connected between the points A and C to provide the power supply to the bridge network. So let us see the description of this D-Sauty bridge. Arm AB, it is having the unknown capacitance C1. So what will be the value of the Z1 impedance? It will be equal to this capacitance C1. Okay. Next we are having the arm So our Z2 impedance, it will be equal to this capacitor C2. Next is our arm BC. Arm BC is an known non-inductive resistance R. So the value of the impedance Z3, it will be equal to this resistance R3. Then we are having the arm CD, which is again a known non-inductive resistance R4. So Z4 is equals to R4. So these are the values of the 4 impedances Z1, Z2, Z3 and Z4. Now when we are representing the impedance, then if we are having a capacitor, then capacitor is represented as XC, and XC is equals to 1 upon J omega C. Okay, and when we are representing an inductor, it will be equal to J omega L. Okay, this is the capacitive reactance and this is the inductive reactance. So when we are having a resistance, capacitor and inductor in a circuit, then before a resistance we take the value of R. For the inductor we take the value J omega L, that is the inductive reactance, and for the value of capacitor we take 1 upon J omega C. Okay, so this is how the value of the impedances will be written. Now this alternating current bridge, it is said to be balanced when the detector, it gives us a null deflection. So when this detector is going to give us the null deflection, it means that the potential of point B and point D, they are at the same potential. There is no potential difference between them and no current is flowing through this detector. Then only the detector will give us the null deflection. Now when the points B and D, they are at the same potential, it means the voltage drop across the points AB and the points AD, they are same. That means voltage drop across AB is what? E1, and voltage drop across AD is what? E2. So E1 and E2 will be equal. Also, when we have studied the general balance equation for an alternating current bridge, so bridge is balanced when the detector is giving us the null deflection, and at the condition of balance we have the famous balance equation, which is Z1 Z4 is equals to Z2 Z3. This is the balance equation for an alternating current bridge. So here also D-Sauty bridge, it is an alternating current bridge. So Z1, Z4, their multiplication will be equal to the multiplication of Z2, Z3. So here we have already written the value of the 4 impedances. So we are going to use this balance equation to get the value of this unknown impedance, that is a capacitance. So we will use the same equation. Z1, Z4 equals to Z2, Z3. This is the equation when the bridge is balanced. So we can write that at balance, we are having this equation. Now putting the value of the 4 impedances here in this equation, Z1 is what? The capacitor. So whenever we write the value of capacitor, we will write it in the form of 1 upon j omega C1. Then we are having the Z4, which is a resistor. So resistance is written as it is, that is R4. Then Z2 is another standard capacitor. So it will be written as 1 upon j omega C2. And Z3 is what? Resistance. So it will be written as it is. Okay. Now here if we see j omega is present on both sides of the equation, so it will be cancelled out. Okay, so we will get the ratio of C1 upon C2 is equals to R4 upon R3, or we can say the value of the unknown capacitance C1 is equals to C2 multiplied with R4 upon R3. Okay, so this is how we can measure the value of the unknown capacitor in terms of a standard capacitor. This is C1 is our unknown capacitance and C2 is our standard capacitor. Now in this D-Sauty bridge, you have seen that this is a very simple bridge. You can easily find out the value, and also the circuit is also very easy for this D-Sauty bridge. But this D-Sauty bridge, it measures the value of the capacitance of the capacitor, which is free from the dielectric losses. Okay, so here we can measure the capacitance of only those capacitors which are the ideal capacitors, that is those capacitors which are free from the dielectric losses. So here the value of the unknown capacitance will be for a ideal, or we can say perfect capacitor, or we can say it is the limitation of this D-Sauty bridge that it measures the value of the capacitance for only those capacitors which are free from dielectric losses. Okay, now if we come to the phasor diagram for this D-Sauty bridge, then phasor diagram, which is the diagram which shows us the relationship between the phases or between the vectors of the various currents and voltages which are there in the circuit. So phasor diagram for this D-Sauty bridge, here in the circuit you can see we are having the currents I1, I2, I3 and I4 which are flowing in the respective arms, and also we are having the voltage drops across these arms. So what is the relationship between the voltage and the current in a particular arm? That will be shown in the phasor diagram. Now before coming to the phasor diagram, one concept should be clear to you, that if we talk about the voltage and the current across a resistance, then voltage and current across a resistance, they are in same phase with each other. So for a resistance R, the voltage and the current, their vectors are on the, or we can say voltage and current, they are in the same phase. If we talk about a capacitor, Then for the capacitor, the voltage lags behind the current by 90 degree. And if we talk about an inductor, then for an inductor, the voltage leads the current by 90 degree. So this concept should be clear to you, then only you can draw the phasor diagram for a AC bridge. So here, if you see, if we are starting for an phasor diagram, first we have to take a reference phasor, and all the other vectors, they will be drawn with respect to that phasor. So here we will take the current I1 as our reference phasor. So I1 will be drawn here on this line. Okay. Now in the arm AB we are having a capacitor C1. So for a capacitor we know that voltage is going to lag behind the current. So current is E1, and if we talk about the voltage, so voltage will be what? I1 upon J omega C1. That will be the voltage drop. So this voltage will lag the current by 90 degree. So this is our current. Voltage will be here I1 upon J omega C1. Now next we are having the AD arm. Here we are having the current I2 and the capacitor is C2. So voltage drop will be I2 upon J omega C2. Now when this bridge is balanced, we are saying that the detector will give us the null deflection, means there is no potential drop, or we can say that B and D, they are at the same potential here, and no current is flowing through this detector. So this I1 current will be equal to I3 because no current is there in this arm. So I1 is equal to I3. Also this I2 will be equals to I4. And also we are saying that B and D, they are at the same potential. It means E1 and E2 will be equals. So E1 will be equal to E2 and E3 will be equals to E4. So we will use these equations in the phasor diagram. E1 we have already drawn here. I1 upon J omega C1 is E1. And this E1 will be equals to E2 when the bridge is balanced. So the value of E2 is what? I2 upon J omega C2. So this I1 upon J omega C1 will be equal to I2 upon J omega C2. Okay. And we can say that I1 and I2, they can be drawn on the same line. Okay. So this voltage, it is lagging the current by 90 degrees. Okay. Next we will come to this E3 voltage drop. E3 voltage drop is across a resistance. So across a resistance it will be equals to I3 R3. Okay. And here I3 is equal to I1. So we can write it as I1 R3. So across a resistor, the voltage and current, they are in the same phase. So voltage is what? I1 R3 and current is I1. So I1 we have already drawn here. So I1 R3 will be here on the same line. I1 R3, or we can say it is E3. And E3 is equals to E4. So it will be equals to I2 R4. Okay. So on the same line we have drawn this current and the voltage because this is across a resistance. Now this was E1, this is E3. So E1 plus E3 is equal to the total voltage drop, and E2 plus E4 is also equal to the total voltage drop, that is E, total EMF. So here if we extend these vectors, these phasors, then we will get the resultant phasor for the total EMF E, which is the sum of E1 plus E3, or we can say it is the sum of E2 plus E4. So So this is the phasor diagram for the D-Sauty bridge. Now, as I have said that this D-Sauty bridge, it measures the value of the capacitance for a capacitor which is an imperfect capacitor, which is a perfect capacitor which is free from the dielectric losses. But this is not a practical case. This is an ideal situation. Okay, so if we want to measure the capacitance for the imperfect capacitors, that is those capacitors which are having dielectric losses in them, then this D-Sauty bridge, this circuit diagram, it will give us then inaccurate results. So the advantage of this bridge is that it is very simple and we can easily measure the capacitance for the ideal capacitors or perfect capacitor. But if we are using the same circuit for imperfect capacitor, it will give us the inaccurate results. So some modifications are done in this bridge, and that bridge is known as the modified D-Sauty bridge, which can measure the value of capacitance for the imperfect capacitors. So let us now study the modified D-Sauty bridge. This D-Sauty bridge is called D-Sauty because it is developed by or invented by the scientist, and it is named after the name of the scientist only. Okay. Now, what are the modifications in this D-Sauty bridge? Let us first see the circuit for this bridge. Capacitor, and this resistance is representing the dielectric loss component of the capacitor. So here we can measure with this circuit diagram, we can measure the value of the capacitance for the imperfect capacitor which are having the dielectric losses in them, because in this circuit the dielectric loss component is also considered. So in arm AB, now we are having the capacitor, the unknown capacitor C1 with its dielectric loss component and also a resistance connected in series with it. So here in this arm AB, you can see we are having the unknown capacitance C1 connected in series with the resistance small r1, which is representing the dielectric loss component and also the resistance capital R1. Similarly, in the arm AD, we are having the standard capacitor C2, which is connected in series with the resistance small r2, which is representing the dielectric loss in this capacitor and also a resistance capital R2. So similarly in the arm AD, And in arm BC and CD, we are having the same non-inductive resistances R3 and R4. So R3, R4 are the known non-inductive resistances. Now, if we talk about the value of the impedances now, so the value of impedance will be Z1, Z2, Z3 and Z4. So Z1 is now changed because Z1 was earlier only the capacitor. Now it is having two resistances also connected in series with it. So now the value of Z1 will become, because resistances are in series, so it will be capital R1 plus small r1 plus 1 upon j omega C1. Similarly, our impedance Z2 will be R2 plus small r2 plus 1 upon j omega C2. And Z3, Z4, they are same, R3 and R4. So the balance equation we are having was Z1, Z4 is equals to Z2, Z3. We are going to put the value of the impedances in this balance equation so as to get the value of the unknown impedance. So R1 plus small r1 plus 1 upon j omega C1 multiplied with Z4, which is what? R4. Z2 is R2 plus small r2 plus 1 upon j omega C2 and R3. Now when we multiply R4 inside, it will be R1 plus small r1 multiplied with R4 plus R4 upon j omega C1. We can write it like this. Also here we can write it like this, R2 plus small r2 R3 plus R3 upon j omega C2. Now in this equation we are having the terms which are having imaginary parts and some terms are there which are having the real parts. So in this term we are having no j omega term, so this is a real part of the equation. This is having j omega, so it is the imaginary part. Again, this is the real part and this is the imaginary part. So in this equation we are going to separate it into two equations. One is for the real part and one is for the imaginary part. So equating the real parts only, we will get the equation R1 plus small r1 multiplied with R4 equals to R2 plus small r2 multiplied with R3. Solving this equation and get the value of the resistances, and if we equate the imaginary parts, from imaginary parts we are having the equation R4 upon j omega C1 is equals to R3 upon j omega C2. So j omega, they will be cancelled. We will get the ratio of C1 upon C2 as R4 upon R3. And from this equation we are getting the ratio of R4 upon R3 as R2 plus small r2 upon R1 plus small r1. So from both the equations we are getting the ratio of R4 upon R3. So our equation will become C1 upon C2 is equals to R4 upon R3, and this is also equal to this R2 plus small r2 upon R1 plus small r1. So through this we can measure the value of the unknown capacitance C1 by in terms of the value of the known impedances. Okay. Also we can compare the value of two capacitances also. Okay. Now there is another term which can be measured, or another factor other than the capacitance which can be measured through this Sauty bridge, and this factor is called the dissipation factor. Dissipation factor is defined as the tangent of the loss angle. And sometimes we can also say that it is the reciprocal of the quality factor. And quality factor, it is the figure of merit which defines the quality or the goodness of the electrical component. So quality factor, it gives us that how much energy is stored in that capacitor, and dissipation factor is just reciprocal of it. So as I've said that this dissipation factor, it is defined as the tangent of the loss angle. So if we measure the dissipation factor for the two capacitors C1 and C2, so for C1 we are having dissipation factor D1, so it will be the tangent of the loss angle, that is del 1, or we can say it is defined as the frequency multiplied with C1 R1. Okay. Similarly, D2 is the dissipation factor for the capacitor C2, so it will be the tangent of del 2, or it will be omega C2 R2. Now from this equation, the equation for C1 and C2, we have got value of C1 upon C2 as Now from this equation, if we multiply C1 with R1 plus small r1 and C2 with R2 plus small r2, we will get C1 R1 plus small r1, C2 R2 plus small r2. So if we write it, multiply this C1 inside the bracket and C2 inside the bracket, what we will get? C1 R1 plus C1 small r1 equals to C2 R2 plus C2 small r2. Now bringing the terms of capital R1 and capital R2 on one side and small r1 small r2 on the other side, we will get the equation as C2 small r2 minus C1 small r1, C2 capital R2, means bringing this C1 R1 on this side and C2 R2 on this side, so it will be C1 R1 minus C2 R2. Okay, this equation we have got. Now we want to find out the difference between the two dissipation factors. So it will be D2 minus D1, D2 minus D1. D2 value is omega C2 R2 and D1 value is omega C1 R1. Now C2 R2 minus C1 R1 we have already got. So if we multiply this whole equation by omega, we will get this term. So multiplying this with omega, we will get omega C2 R2 minus C1 R1 equals to omega C1 R1 minus C2 R2. So the value of this will be omega C1 R1 minus omega C2 R2. Okay. Now from this equation, if we take C2 as common, we are left with C1 R1 upon C2 minus R2. Now the value of this ratio C1 upon C2 we have already obtained. C1 upon C2, this ratio is also equal to R4 upon R3. So we can put this value here also. So omega C2 R4 upon R3 into R1 minus R2. So the value of this dissipation factor, or we can say the difference between the dissipation factors of the two capacitors, will be omega C2 R1 R4 upon R3 minus R2. This is the equation for the difference between the dissipation factors of the two capacitors. So using this Sauty bridge, we can not only measure or compare the value of the capacitances of two capacitors, we can also compare the dissipation factors for those capacitors. Now coming to the phasor diagram for this modified Sauty bridge. So in the circuit diagram for the modified Sauty bridge, we were having one resistance, capacitance, and another resistance in this AB arm. So again we will take the reference phasor, that is I1. Now we are having the resistances here, that is capital R1 and small r1. So across capital R1 we will be having I1 R1, and across this we will be having I1 small r1. Okay, and across this capacitor we will have I1 upon j omega C1, and across this we will have I2 upon j omega C2, I2 R2, I2 small r2. So this is, if we sum up this will be equals to the total voltage drop E2, and this will be equal to, sum of these will be equal to the voltage drop E1. So here we have drawn this current. This is I1. Okay, so I1 R1 will be drawn on the same line. I2 R2 will also be drawn on the same line. Then we are having I1 small r1 and I2 small r2. Now for the capacitor, it will lag behind it by 90 degree. That is I1 upon omega C1. Okay, and I2 upon omega C2 will also be this. So if we, when we say that the bridge is balanced, it means the voltage drop E1 will be equals to E2. So here E1 is this and E2 is this. So their resistive parts will be equal and their capacitive parts will also be equal. So capacitive part we have drawn here and resistive part is drawn here. So I1 and I2, they are drawn on the same line, and the voltages across the resistance and the currents, they are in the same phase, and the voltage across the capacitor, it is lagging behind the current by 90 degree. Now if we take the resultant of these three vectors and these three vectors, so it will be equal to E1 and this will be equal to E2. So extend these lines. If we extend them, we will get the resultant voltage, that is E2. And if we extend this I1 R1 and this I1 small r1, we will get the voltage I1 omega C1 plus this I1 R1, I1 capital R1, we will get E1. Okay. Now E1 plus E2, if you see in this E1 plus E3 and E2 plus E4, it is equal to the total voltage E. Now if we talk about this, I1 is also equal to I3. So voltage drop I3 R3 can be written as I1 R3, that is on this same line. Okay, and here we can write it as I2 R4. Okay, that is on the same line. So if we extend this, we will get the voltage E, which is the sum of E1 plus E3, or we can say E2 plus E4. So this is the phasor diagram for the modified D-Sauty bridge, and this modified D-Sauty bridge, as it is considering the loss component, the dielectric loss component also, so it can be used for the measurement of the capacitance for the imperfect capacitors. So here in this video we have studied the measurement of capacitance by using the D-Sauty bridge and also the modified D-Sauty bridge. We have studied the phasor diagram also for both the bridges and how we can calculate the dissipation factor for the capacitors using this bridge network. So I hope that this topic is clear to you. Thank you.